Okay, so we've had a little bit of an introduction to what energy is, and we've talked about work, which is where energy comes from. So now we're going to dive a little bit further into the different forms of energy and talk more specifically about the three main ones that we're going to be working with. So in this video, he gives a few different examples of all the different types of energy and a couple of little quantitative, qualitative questions, just kind of introducing the types of energy and thinking about them mathematically. And let's get into that. We'll get into that right away in this section. So the first main type of energy that we're going to talk about is kinetic energy. And we've talked already. This is symbolized by the letter K. You might see it sometimes also symbolized as E subscript K for kinetic energy. This is associated. This type of energy is the energy that's associated with motion. So we know that it has to have a velocity, and that's about it. That's about all we know right now. But let's dive in right now a little bit more. Okay, so we've taken a look at the energy skate park as an introduction to this. But if I think about the skater as he's going up and down the half pipe, when he's at the bottom, that's when he has all kinetic energy. And when he's at the top, that's when he has all potential energy. And if I think about what happens, this is where he's got the largest velocity, and this is where he has... I guess this is up at the top of the ramp is where he has zero velocity, and that's why he changes direction and goes back down. So we can see that fluctuation a lot between potential energy and kinetic energy, and we'll see that a lot throughout this unit. But kinetic energy itself is the energy of motion, which we talked about. And we're actually going to talk about two different types, and this will get a little bit confusing, but when we come back to it later on in Unit 5, hopefully we'll clear up some stuff. So there's two main forms. There's translational kinetic energy, which is just going around a straight path. And then there's also rotational kinetic energy. And this is for anything that's pivoting around an axis. And I'm going to do a demo in class that will really show this and really help us see this. But the translational one is the one that we're going to see the vast majority of the time. And that has this formula. It's a pretty simple formula. It's 1/2 mv squared. So 1/2 times the mass of the object times its velocity v squared. Now what that does, a quick little note about that, if v is negative, that's going to go ahead and make it a positive. So energy is not a vector quantity. It just says how much it has. So not a vector quantity. You do not see direction. You only see the magnitude. Okay? And then we also have rotational kinetic energy. And this is, it gets a little confusing because we haven't talked about any of this yet, but it's an object with a moment of inertia I and angular velocity omega. And a moment of inertia, it's not, if you notice, these are directly parallel. I goes with m and omega squared goes with v squared. So I is the moment of inertia, and that's not how much mass you have, but rather how your mass is distributed. And then omega, instead of being the linear velocity, is the angular velocity. It's how fast it's rotating. And like I said, I'll do a demo in class that hopefully clears that up. So this is the ring versus the disc demo, which we'll look at later on in the year. Essentially, I'm going to have two inclines, and down those two inclines, I'm going to have a ring which has all of its mass concentrated on the outer edge, and it's going to be facing a disc. This is the greatest drawing ever known to man. It's going to be essentially competing against a disc, which has a uniform mass distribution. And the question is, which one's going to win, and why would it win when before we've talked about acceleration in the x direction is always g sine theta. So we'll take a look at that during class. All right, so I got a quick check. We have ball A has half the mass, 1/2 the mass, and 8 times the kinetic energy. So what's the ratio? Well, if it's half the mass, it's going to have 16 times this v squared concept to make up for that, which means that velocity is going to have to be 4 times as much. So if I have 4 times the velocity, it's gonna make a big difference. The faster you go, the more kinetic energy you have. And then rotational kinetic energy, that's just a way of expressing the sum of all. If I have this whole axis here, this area is going with some velocity, this area is going with a different velocity, this area is going with a different velocity, and the rotational kinetic energy is a sum of all of that. In rotational kinetic energy, the moment of inertia, so remember this was 1/2 I omega squared. The moment of inertia is I, takes place of the mass, and the angular velocity takes place of the linear velocity. So it does not matter how massive something is, but rather how that mass is distributed. So like I said, we'll take a look at that later on in the year, but we'll do a quick little demo in class. Right, so we have an example problem. Two-man bobsled has a mass of 390 kilograms. Starting from rest, the two racers push the sled for the first 50 meters with a force of 270 newtons. Neglecting friction, what is the sled speed at the end of 50 meters? So we'll take a look at this in class, but we've talked about how work equals the change in energy. So in this case, the work equals the change in kinetic energy, and we talked about work in section 2, so work is force times distance, and kinetic energy is going to be 1/2 mv squared, and we're looking for that velocity, and we'll do that in class. Another quick check, a light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter starting from rest. After the force is removed, the kinetic energy of the light plastic cart is blank that of the heavy steel cart. So take a second and think about that. And if you want to, you can pause it. And I'm going to go ahead and answer it now. The answer is they are equal to. And you're saying, wait a second. The heavy steel cart has the same energy, kinetic energy, as the light cart? And absolutely. They're pushed with the same force for the same distance. And work is our change in energy, which is force times distance. So yes, they get the same energy. But this one right here, higher mass, lower velocity, compared to this one, lower mass, higher velocity. But their amount of energies are the same. So that's actually going to sum up our quick little introduction to kinetic energy. We will talk more about kinetic energy as we get used to utilizing it in equations. But again, the one big key takeaway, kinetic energy is 1/2 mv squared. And we'll be using that throughout the course of this unit. And we'll be taking a look at different energies in the next section.